want to introduce the next speaker, who is Fabio Ribeiro. I have the fortune to be sharing the same office while during the days at Berkeley when I was working with Heinemann. He's working with Gabor Samajai, and he's going to talk about some dechlorination of hydrocarbons.
Good afternoon all. It's a pleasure and an honor to be here to celebrate the life of Dr. Heinz Heinemann. As Jung Peng mentioned, I met him when I was a postdoc at UC Berkeley, and I was working on a problem that Professor Weiss mentioned, which is hydrocarbon reactions, and he was an expert on that. He was the one that developed, he was even shown some of the original work. And we were working on that in single crystals, and I had an opportunity to talk to him many times about that particular chemistry, and was great for me. I had heard about him. Of course, he was the founder of Catalysis Reviews, a very important journal, and he was very well known in catalysis, so I was very glad to have the opportunity to talk to him. And I even have a problem that he was the person that started all that, so I was very happy to talk to him, and we had many conversations and so on. But the really question that I wanted to ask him was the secret of his longevity. He was over 70, and he was very much interested in his work, and I was amazed of somebody like that. Then I wanted to find out what's the secret of his life and what he was doing, and how he could be doing all those things. And at that time, he always would get some award, and I had the opportunity to read about his life, and I thought that maybe he had lived so long because his life was very easy. But then I found out that quite the opposite. His life was very difficult. He has always problems in his life. And then I asked him how he could do so well in life, and that was the one lesson that I still, today when I have a problem, I think about him. All the problems that he had and how he handled it was absolutely, he was amazing on how he could be doing this in addition to all the catalysis. Maybe everything that he has done comes on that, the way that he handled life. In particular, when I was in Berkeley, he lost his wife that had been with him for 43 years. And I thought that after that he would not come anymore, he would be completely out. And I was amazed to see how he could rationalize that and go on with life. And I'm sure that that's, looking back on his life, that's what he's done. So to me, in addition to all the discussions in catalysis, that was very important to me. So what does that hydrodechlorination have to do with Dr. Heinemann? Is in a sense, in petroleum industry, he started putting rationalizing on this very complex chemistry. If you look at the real feed that comes into a refinery, there's thousands of compounds in this particular process called catalytic reforming that he worked on. How would you design a reactor and think about it if the feed has thousands of compounds? Well, what they did is they took a model compound and they took a family of molecules, and they understood the chemistry on that particular family, and then from there they could understand all the others by picking the important parameter. What is it that I have to know about this molecule, so that if I have a really complex mixture, I can understand what's going on. So this type of work is dedicated to him in his memory, and it's a similar approach. The reaction we are talking about is called hydrodechlorination, which is you take a molecule that has a carbon-chlorine bond, and you react with hydrogen, and you make a carbon-hydrogen bond and HCl. This is usually done under the presence of noble metals, and one of the most active metals is palladium. Of course, the motivation for doing all this is really not this reaction itself, but it's to understand the catalysis. So here are the two problems in catalysis, right? We always think about rate and selectivity. So if you look at those two isomers here, I would ask you first, what's the rate of hydrodechlorination? Not think about what products I'm going to get, but what's the rate that those molecules are going to react. And you may say, well, probably not very different. Just because we have the two chlorines in different carbons, but the answer is that it's very different. It's about a factor of 3,000. This is the most reactive. And one of the objectives of this talk is, as I told you, if you have a family of molecules that you have carbon and chlorine, and you can have thousands of them, and you have so many of them, and the rates vary so much that you want to have a theory so that you can rationalize. So I want to do those two things, rationalize the rate and selectivity. This one here, I'm going to show you that we did very well. And in fact, I can tell you that if you tell me what's the strength of the carbon-chlorine bond, I can tell you what the rate is very precisely, because the rate determining step is breaking that carbon-chlorine bond. And if you know that, then you know what the rate is. Now, the second question, we have absolutely no clue the selectivity. Now, you cannot even explain, not even talking about predicting what it is. Even if we know what the selectivity is, it's magic up to now. And its catalysis is not there yet, but we are trying to understand what's going on. So I'm going to tell you then the objective of this talk is talking about rate and selectivity. And rate, basically, it depends on the carbon-chlorine bond strength. And selectivity, I don't know what it depends on, but maybe you can help me. So here's the case of selectivity. Take this molecule here again. Take this molecule again. So there are three products on this particular reaction. This one here goes 84%, 12%. This is the desired product. You lose the two chlorines, underhydrogenated and hydrogenated. It turns out that palladium always does that, no matter what size of palladium, if it's small particles, big particles, single crystals, it always does that. And the question is why, and how can you control this? This is actually was the objective of this project, to see if we could have a palladium catalyst that could do that, this particular reaction at 100%. So this is the problem, how to explain that, or it would be nice if we could predict, but even how to explain why palladium does what it does. And we'll see what we can understand on that. So the strategy here, as I mentioned to you, was to take a family of compounds. So you take one that has carbon-chlorine compounds, carbon and hydrogen, and the other one that has fluorine, and then you can study the selectivity and rate on those and see how if we can learn about those reactions. So what do we know about the reaction? This is the experimental methods. We use a well-mixed reactor, a CSTR, so we can do kinetics on that, and we have a mass spec connected to that, so we can do isotope type of experiments. The reaction is structuring sensitive. Here is an example for this particular hydrocarbon, which is the one that's CF3CFCl2. There are three different compounds. And here what happens is we have a single crystal, 111 and 100 coil, or a palladium of carbon. Professor Somajai did some work on that, on the series that I showed to you after that, and all of them show that the rates for the three different compounds, the selectivity are not very dependent on if you have a small clusters or a single crystal. So it doesn't depend on the structure of the catalyst. So we knew that. The selectivity also doesn't depend on the conversion. Here's a plot of conversion and the selectivity. If you go 1% conversion or about 20% conversion, the selectivity is the same. So that means that the molecules absorb on the surface and then they react. And once they dissolve, they never come back, because actually the products are much less reactive than the reactants. So we know that all this is not a sequential reaction that you first put one hydrogen and then two hydrogens and then three, but they absorb on the surface, and that all happens on the surface. So once the molecule absorbs then on the surface, it will never come out, but as a product. So this is the reactions proceeding parallel. And then a simple step then for this particular reaction of what's going on is that you may think, well, this molecule absorbs on the surface and then can pick up one hydrogen and then lose another chlorine and second hydrogen and third hydrogen. And one question that we wanted to ask, if what are the steps that are reversible? And we can do that with an isotope. It turns out that this molecule here, HCl, you're breaking, instead of carbon-chlorine bond, you break a hydrogen-chlorine bond. That's much easier to break. So it happens that if you add chlorine-37 to your mixture, because it absorbs, this is in equilibrium, the surface will be all chlorine-37. So when your molecule comes down and absorbs on the surface, then you can tell if this reaction here is going to be reversible, is the molecule comes and breaks. If it comes back, then the surface is going to be mostly chlorine-37 because the equilibrium between HCl. And then you can tell by looking at the isotope distribution of this molecule if this particular step is reversible or not. So in this case, it turns out that if you run this reaction and you look at the isotope distribution of the reactant, there is absolutely no difference. You get always the natural abundance, which means that this step here is irreversible. Now, if you look at the next step, which is once the molecule is absorbed on the surface, you would like to ask if this particular step is reversible. So you do the same type of experiment. If this is reversible, then when this molecule here hydrogenates, it will be enriched in chlorine-37. And it turns out that this particular step here then is reversible. So once the molecule absorbs on the surface, it never desorbs. So that the first step is irreversible, and the other steps on the surface are reversible. So the molecules then, once on the surface, they can exchange chlorine back and forth. So this is important to understand selectivity. The other reaction that we are interested is in hydrodechlorination, you have a hydrogen and you have HCl. And it turns out that there is an equilibrium that I already told you that this is, assume that this was very fast, so that this is in equilibrium. And we wanted to compare what is the rate of this reaction here, back and forth, compared to the overall reaction, which is hydrodechlorination. So it turns out that if you use deuterium isotopes again, then you can measure what is the rate of forward and reverse for this particular reaction. If you put deuterium instead of hydrogen and you look at the concentrations of deuterium and hydrogen. So if you run this experiment and you look at the deuterated chlorine-37, the rate of formation of D37 is this much, and the rate of hydrodechlorination you can measure at the same time. And then you find out that the forward and reverse rate for this particular reaction, they are 400 times faster than the rate of hydrodechlorination. So we know that that particular step there is equilibrated. It's a very facile reaction on palladium. So now if you know all those things, then you can propose a mechanism. And the mechanism is that the hydrocarbon, when it absorbs on the surface, it doesn't dissociate, so it can come back and forth. The molecule doesn't, the carbon-chlorine bond doesn't break. But eventually, this carbon-chlorine here bond breaks in one side, and there's something that happens kinetically. We don't need to know what that is. You want to know what the rate is. So the rate expression then is equal to the concentration of this, which is equal to the concentration of this times that. It's just studying your machine. Then I told you that those two steps here are equilibrated, and if that's true, then and also that the chlorine is the most abundant reaction intermediate because it binds on the surface much more strongly. Then from those two expressions, you can find out what's the number of free sites. You put back here, then you get your final expression. So this is the rate of hydrodechlorination, and it turns out that for the series of compounds I showed to you, including those series that I'm not showing here today, but it's the same thing, they all follow this particular rate. So that's interesting, and the next thing we're going to do is we're going to measure this rate, those two, the rate constant that appears in the rate determining step and the equilibrium constant, which is this overall equilibrium here. And we'll see if this mechanism is right. Let's see if all this thing makes sense. And then you can do that easily by linearizing that rate that I showed to you, or you use a nonlinear estimation to calculate this K and that K. And you get a plot like this, and from the slope and the intercept you can calculate those constants. And you can do that at each different temperature. So you do that for 4 different temperatures, and you can do that for each of the series of families that I showed to you. Then here is the typical Arrhenius plot, that it should be like this. So as the temperature goes up, the rate goes up. And the equilibrium constant should go down as the temperature goes up. And this is, so that's all reasonable. So that happens with this particular mechanism. So if all this is right, then you get, if you plot now the carbon-chlorine bond energy, which you can look in the table, versus the activation energy, which is experimentally determined, that was the K that I just calculated. Then there is a Polanyi type relationship, which is what you would expect. And then if you plot K, which is the rate, the equilibrium constant in this particular equilibrium, of course this particular equilibrium doesn't depend on what kind of hydrocarbon you have. You should get the same delta H, which you do experimentally. So this doesn't prove the mechanism, but shows that everything makes sense. So then the next step is we wanted to understand more about the chemistry, and we would like then to use some theoretical methods to see what happens when the molecule like a CF3Cl absorbs on the surface, what happens. And then this is the work with Dr. Luis Barbosa using VASP. I'm not an expert on that, but we work together on this, and he uses a surface model, 5 metal layers with 9 metal atoms. We always be using the 1110 of palladium to model this, and he can then model the absorption, the various geometries. This is a palladium 110, so this is the atoms on the top. This is the trough here in between, so he can model all types of geometries that this molecule has, and you can calculate relative stability and the heats of absorption for those molecules. And we can also calculate transition states on that, the real kinetics, what happens if you have a long bridge type of reaction, or if it's a short bridge or on top, so if the molecule is on top and then it dissociates. Very different activation energy, and then this is not experimentally, but this is what's predicted with theory, the bond energy versus the dissociation energy, what happens on that type of reaction. So we did all this, we are thinking about the selectivity, I told you, to understand what, if we can find out what happens on this particular reaction. So here is what we can do, as I told you, with rates. Here is the normalized rates for the 2 families. You can see that 5 orders of magnitude here, 7 orders of magnitude here. And for each family, I need to have one adjustable parameter. This is a Polanyi type of relationship that I showed you that experimentally and theoretically works. And this is what we calculate, and this is what's measured. And you can see 10 to the 5 and 10 to the 7, we make a pretty small error, about a factor of 4. So 4 in 10 to the 7, that's excellent. So if you tell me what's the carbon-chlorine bond strength, I can tell you what the rate, very precisely, but this is the overall rate of reaction. So we do very well in predicting what's the overall rate, and we know what the kinetics is. So if you're designing a reactor that you just want to react those compounds, then we can do very well, because I know the kinetics, I know how the rate varies as a function of all concentrations and the carbon-chlorine bond strength. Now the big question then, the next question is the selectivity. But all I showed to you right now were 3 steps. This is the rate determining step, and I told you that there are 2 steps that were equilibrated. That's all you need to find out about kinetics if you want to know the overall kinetics. But if you want to know product distribution in this particular compound, then we can't do that. Those are the 3 red ones, is the ones that I've been considering. Those other steps are not kinetically significant in terms of the overall rate, but if you want to understand the kinetics, you need to know the rate constants for each of those steps. If you want to predict what is going to be the concentration of this, that, and that. And I told you that experimentally this is about 15%, 75, and 5%. So that's what we would like to predict, and then we wanted to use theory to do that. Then if you take this, our first try, this molecule here, there is only one product observed, which is CF3H, and you can understand why there is only one, because once you take this one chlorine here, which is quite exothermic. To take the second one is pretty endothermic, and you can easily put a hydrogen on that. So it's easy to understand that if you take this molecule and you get only on one product experimentally, that's what we see. But if you go to the next one, which is CFG, CF2CL2 is not even obvious why you have only two products. Methane, it either loses all the hydrogens or only the two chlorines. And I'm not going to show you the details here because there are literally hundreds of those thermochemical diagrams, but we couldn't. The problem with this is, as I'm going to show to you next, is those calculations here. If you want to do those type of calculations, you have to assume what's on the surface, and it's very sensitive of what is on the surface. The coverage determines very much the thermochemistry. So if you take CF2 going to CF, and you assume that you have two chlorines or two hydrogens, you get -10. If you assume you have one chlorine and 3 hydrogen, you get +2. So it's very different. So without knowing what the coverage is, which means reaction conditions, you can't, even if you do, this is only thermochemistry, you can't predict what the energetics is. And if you make, of course, a mistake of 12 kilojoules per mole, you're never going to be able to predict the selectivity that I told you. So this is a challenge for theory, and those calculations are already very expensive. You can't possibly go through all of them. And how can you predict what's going on, or even explain on this particular reaction if you wanted to find out what's the selectivity of this reaction? But we can tell a few things. I told you, I'm not sure if you caught that, but I told you that this is the reaction that we're very proud of, and we say that we need only one site. But the theory, my theory friend told me, no, you need 2 sites, and all the calculations I showed to you, he used an empty surface, and then it turns out that the molecule prefers to absorb like this. So theory is telling us you need 2 sites, and here's one site, so it doesn't, there's a problem. And the problem is very easy to understand, is the coverage on the surface. If you have a surface that has no chlorine, it's empty, and if you absorb a molecule that has 1 chlorine and 3 fluorines or 3 hydrogens on top, it's -23 kilojoules per mole. But now if you absorb that on 2 sites, -35, it prefers that, and then when you dissociate, you get this. But if you put chlorine on the surface, and if you try to absorb a molecule, so think about this, by the way, as this is the unit cell. So you will repeat in an infinite on the calculation. So this is the unit cell there. So there will be chlorine over and over. So if you try to absorb the molecule with using 2 atoms, it's +26 because the chlorines give you a lot of repulsion. But if you absorb on top, it's endothermic. It's exothermic. So that's why on the real catalysis, I told you that the surface is full of chlorine. The molecules like to absorb in this way, and that's why if you do your calculations on empty surface, you can't get the right answer. You have to do it with adsorbents. So the adsorbents on the surface is critical to understand the catalysis. So all this catalysis is done on a very crowded surface, and this is critical to understand what the chemistry is, and including all the calculations. But of course, this makes the calculations much more complex, but tells us why is that you need only one site on the real reaction conditions, not 2. So for conclusions, in general, if you hydrodechlorination, all the molecules we tried, and we tried 3 families, I showed you 2 families, they all follow this particular simple linear initial, and we showed to you that those things make sense. You can actually calculate those rate constants, and the all kinetics make sense. The rates correlate very well to carbon-chlorine bond energy, so if you know the carbon-chlorine bond energy, you know what the rate is going to be. The reactions are going parallel. The adsorption is irreversible. Once the molecule absorbs, it goes to products, never comes back. The number of sites in the rate determining step is 1, and that's why the reaction is structure insensitive. So if you try any type of palladium, it doesn't matter what it is, because the chlorine erases any differences that you have on the surface. As I told you, the surface is covered with chlorine, but the prediction of reaction selectivity is still a challenge. This is one of the examples in catalysis. The other one would be NO oxidation or CO oxidation, where the surface is completely crowded. CO oxidation with CO, NO oxidation with oxygen, and that dominates all the chemistry. So if you really want to understand the chemistry, the catalyst is not palladium, but it's a chlorinated palladium surface. Well, with that, I would like to, those are some of these sponsors, and I would like to thank you again for the invitation.
To industrial process. Okay. And also you may know that this dehydrodechlorination reaction became very important after the Montreal Protocol, by which all countries had to destroy the freons, not produce any more, if possible, carbon tetrachloride, or the one being produced by some processes which will not be, stopped at once. You had to get rid of the carbon tetrachloride, which had a negative value. Very good. And the question is, that's okay, but you never mention the life of the catalyst. Of course, I did work for this for quite a few years for a company working in chlorinated solvents, and we found that, of course, palladium was the best on active carbon. But the question is that the catalyst life was not, when you work in the gas phase, it was a difficult thing because it deactivated very, very, very quickly. Can you give me an idea? You ever found the activation of your catalyst? And secondly, when we did work on the liquid phase, then we did improve very much the catalyst life because all the junk being deposited on the surface was extracted by the liquid. So please tell me something about catalyst life because if you have overcome that, it's a big, you have a big thing.
Yeah, no, the idea, of course, on this project was exactly what you said, to get rid of chlorinated compounds. There are so many of them. If you think about it, if you have two carbons, one hydrogen, two carbons, and you can put hydrogen, fluorine, and chlorine, I think you can make thousands of different compounds. And if all of them, if the rate changes so much, you would like to have a theory so that you could understand. So if you have a mixture, then you know what you get. So the beauty of this, by the way, was that contrary to the reactions that Dr. Hyman and co-workers they had to work, hydrocarbon reactions, those deactivate, like it's very difficult to do kinetics. Those are absolutely rock stable. We could do reactions and the catalyst would be very, very stable. But of course, stable in we would run this for a few days, not like in an industrial setting. So we are not thinking about industrial applications. Our friends at DuPont and Dow, those are the guys that do the real thing. We do the kinetics and help them. But there must be some minor or other clues that on the reaction pathways that probably deactivate the catalyst by forming carbon, or depending on your temperature, how much hydrogen you have, and your reaction conditions. We didn't explore that reaction. There was more.
Well, if you say that you could run for days, that's extremely good. Not enough for an industrial process, but pretty good. Thank you.
Okay, we'll stop here. Let's thank